Alrighty, IB Juniors, Unit 1.4, Where Functions Meet. This one's going to be short and sweet, my folks. Basically, graphs can cross each other sometimes, and they can do it in at least 3 ways. But our authors are specifically talking about when quadratics meet other things. And we're really just looking like quadratics meeting other quadratics or quadratics meeting a line. So what we've got here is a line crossing right through the quadratic, using that term cutting like it does with the x-axis. It means it goes right through. Touching, meaning, well, the curve glances off of the straight line and doesn't go all the way through it, kind of like when your vertex is on the x-axis. This is known as being tangent. This line is tangent to the curve. That's how you would describe that. And this one, well, they don't cross each other at all, so they just completely miss each other. Okay, that's all there is to it. Now we're just going to do some examples. It says to find the coordinates of the points of intersection of the graphs that have this equation and this equation without using technology. Well, the only way that two graphs could actually touch each other is if they exist in the same point in space, which means at that exact place they have exactly the same value, aka set them equal to each other. X squared minus x minus 18 equals x minus 3. And since we're doing this algebraically, the only way that you can solve a polynomial is if it is set equal to 0, which means we need to subtract x and add 3. Subtracting x to the left side gives me negative x minus x, or negative 2x. Negative 18 plus 3, because it would be adding it over, it's going to give me minus 15 equals 0. I was going to factor it. Are there two numbers that multiply to negative 15 that add to negative 2? Yes, because if there weren't, this would be a very bad example, right? Two numbers that multiply to negative 15 that add to negative 2 are negative 5 and positive 3. There it is. That gives us two solutions for x. Two solutions for x. That gives us x equals positive 5 and x equals negative 3. But here's the thing. Tricky, tricky. It didn't say solve for x. It said find the coordinates, which means that's only half of the answer. You need the y that goes along with it. Well, since we have x, all we have to do is plug in y to figure out what, plug in x to figure out what y is, and I strongly suggest doing it there because it's going to be a lot less work. It'll be pretty darn easy. So let's see what our solutions are. 5 comma, let's plug it in. 5 minus 3. Whew. Real serious mental exercise there. And negative 3 minus 3, negative 6. I don't know if you guys can hear my cat, but he is meowing on the floor at me. He wants to know why I'm not in bed because it's after midnight. Anywho, those are the two coordinates for the points of intersection. Boom. All right. For our next example, we're dealing with two quadratics. Part A says, yeah, solve this equation. Okay, fine. Challenge accepted, part A. We're going to want this thing to be set equal to 0, right? And since x squared is, hey, there's more of them over here, there's 2 of them, I'm going to move this entire quadratic to the right. So I'm going to subtract this x squared, 2x squared minus x squared. 2x squared minus x squared just gives me x squared. I'm going to subtract this 5x, 2x minus 5x. And I'm going to subtract this 6, negative 4 minus 6. So, again, factoring. Are there two numbers that multiply to negative 10 that add to negative 3? Of course there are. Negative 5 and positive 2. This one just says solve for x, so there's no plugging back in. We legitimately just write, oh, well, x equals 5, and x equals negative 2. Done. So what's going on in question B? Well, question B is the exact same algebraic setup, the only difference is it doesn't say equals. It says is greater than. So, okay, it's going to be this exact same equation. It's just that this symbol won't be an equal to sign. It'll be a greater than. We'll say 0 is greater than x squared minus 3x minus 10. But if you read it backwards, it says that that quadratic is less than 0. Oh, the quadratic is less than 0. Okay. So x minus 5 times x plus 2 is less than 0. Guess what kind of numbers are less than 0? Negative numbers. Our quadratic that we ended up with does have two, we call them critical values, x equals 5 and x equals negative 2. And the way we solve a polynomial inequality is by putting our critical values on a number line. Picture not drawn to scale because nobody cares. And we notice that these two solutions for x, and by the way, they're not solutions to the question, but these two critical values for x, they cut our number line into 3 distinct zones. So all we have to do is test the zones and see if those zones result in positive or negative answers. Let's find out. Let's grab a number to the left of negative 2, like negative 3. Negative 3 minus 5 is a negative number. Negative 3 plus 2 is a negative number. Hold on, I have to kill my cat. Get down. Jeez, sorry. Anyway, what was it doing plugging in negative 3? Yeah, negative 3 plus 2 is also a negative number. If you were to multiply those two negative numbers that you would have gotten had you plugged in negative 3 and realized we don't care what the value is, we just care that they were both negative, you would have ended up with a positive result. Now, you can check any number between negative 2 and 5. Just grab one. 0 is easy. 0 minus 5 is negative. 0 plus 2 is positive. And when you multiply a negative number with a positive number, you will always get a negative result. And then grab a representative to the right of 5, like 6. 6 minus 5, that is a positive number. 6 plus 2, that is a positive number. And multiplying two positives will always give you a positive. We were hunting for the numbers that were less than 0, also known as the negative numbers. So our answer set is coming from right here. However, the numbers negative 2 and 5 are not solutions because at negative 2 and 5, it equals 0, and 0 is not less than 0. So when we write these in interval notation, we just don't include the negative 2 or the 5, so we say from negative 2 to 5, not included. And then the last example, I told you, short and sweet. We have a line of some sort with an unknown constant, and then a quadratic. And what we know is that this line is tangent to the quadratic. Oh, there's only going to be one solution. Now think like an IB student. I just told you a quadratic setup has one solution. The thing that should be jumping to your brain the moment you start talking about how many solutions quadratic things have is the discriminant. Now, if it's tangent, that means that line does touch that curve somewhere in space. And we cannot solve equations like this unless they're equal to 0. So we have to subtract 2x from both sides. Negative 3x minus 2x gives me negative 5x. And I'm going to subtract k. And if it would help you, realize that 4 is a constant, and so is k. So 4 minus k, that's another constant. This term is your C value. And since we're having tangency, we're talking about one solution. So what we know is that our discriminant had better be equal to 0. That's how you get one solution. So let's plug it in. Our B term is -5. A is 2. C is 4 minus k. And let's get to distributing. I'm running out of vertical space, so I'm just gonna scoot over here. -5 squared is 25. And then here, this is a -8 that I'm distributing across here. So -8 times 4 is -32. -8 times -k is plus 8k, still equals 0. 25 minus 32 is -7. And let's get k by itself. Add 7 to both sides. And then divide both sides by 8. And you find that that unknown constant is 7/8. Fun in a bun. Awesome.